Alright, I wanted to make a conceptual video about finding critical points and figuring out whether they're maxima or minima, figuring out whether they are local or global, otherwise known as absolute maxima or minima, and then I also wanted to talk about several different things that the second derivative can tell you about the graph. So I'm starting out with this nice simple one. It's f of x equals x squared. This is what the graph looks like. If I take the first derivative, f prime of x equals 2x, and I set it equal to 0 because at a minima or a maxima, the tangents, the slope of the tangent line at that point will be 0 for open intervals. And so whether it's a maxima or a minima, we don't know immediately, but we do know that if the derivative represents the slope of the tangent line at any given point on the graph, that means that if we set it equal to 0, we will be able to solve for where things stop going up and start going down, or where things stop going down and start going up. Because you cannot go from here to here on a continuous graph without hitting a slope of 0. And so that's what we're looking for by setting the derivative equal to 0. In this case, it's quite nice, x equals 0. And we can tell by the graph that at the point x equals 0, that there is a minima. But if we were blind and we couldn't look at the graph, here's how we would do it. The second derivative of something is the rate of change of the slope. So what that's going to tell you is, in general, is the slope increasing? We call that concavity up. Or is the slope decreasing? And that's called concavity down. Now, if the slope is increasing over time, so the slope is increasing over time, and not even time, I'm sorry, as the slope increases as we go from left to right in the x values, if the rate of change of the slope is increasing, then you'll notice that the point that I go through at the bottom here is going to be a minima. And so when we have a positive second derivative for the value x that is a critical point, we have a minima. And if the slope is decreasing as we go from left to right, then we're going to have a maxima at that critical point. So we have one critical point to analyze. It's x equals 0. We're going to go ahead and take the second derivative, f prime prime of x, which is just 2. Well, that's cool because that's a positive number, and it turns out that with a quadratic, the rate of change of the slope is actually constant the whole time. And so this is increasing at a constant rate. And because it's 2, that means it's the rate of change of the slope is positive, which means that we have a local minima. So a positive number for your second derivative when x equals 0, or when x equals a critical point, is going to represent a minimum. So using the second derivative, we've proved it's a minimum. Now the question is it an absolute minima? And to figure that out, we'll look at the graph and we'll see, is there any point on this graph where we have any output smaller than 0? Because when we plug in our critical point here, we end up with f of 0 equals 0. And we'll notice that there is no way, because if you square negative numbers, they're just positive numbers. If you square positive numbers, they're just positive numbers. There's no way we're going to get a number less than 0. And so not only is this a local minimum, it is an absolute. Now the question is, do we have any absolute maxima? And the answer there is no, because for every point on the graph I can point at and say that's pretty high up, there is another point on the graph even closer to infinity that is larger. So there is no absolute maximum on this graph. Now I'd like to give you an example of when there would be an absolute maximum, because I've made this mistake in prior videos of assuming that an absolute maximum could be infinity, an absolute minimum can be negative infinity, and that's not the case. So what if I'm looking at a closed interval? What if I am only curious about this graph when x is, say, equal to or greater than negative 2 or less than or equal to 3? So now I'm limiting my graph between x equals 3, which is right here, and x equals minus 2, which is right here. So I'm cutting off these parts of the graph and acting like they don't matter anymore. So I'm only interested in what's between this domain. Well, now we actually do have two local maxima. One of them is right here, and one of them is right here. And out of those two, the one that is the absolute is the one that has a higher output, which is this one. So now our absolute maximum is at x equals 3. Our absolute minimum is still at x equals 0, and then we have a local maxima at x equals minus 2. And that could be it's very tricky, a lot of semantics there. The weird part about this is that setting the derivative equal to 0 only gives you the maxima and the minima that are not on the domain edges. So once you're done finding all the things that equal 0 with your derivative, you have to understand that, for example, the tangent slope at this point is not 0. Neither is it 0 here. And so the domains can slip through the cracks. And so whenever you know what your domain edges are, always check those to make sure that they are a maxima, a minima, an absolute maxima, or an absolute minima, because those will slip through the cracks just setting the derivative equal to 0. Now for this problem, this is just the same parabola but upside down. If we take the first derivative f prime of x, we end up with negative 2x. And once again, if we plug in 0 for the derivative, because we want to figure out when the tangent slope is 0, we will end up with 0 equals minus 2x. So x equals 0. We have a critical point at x equals 0. Now to find out if we are concavity down or concavity up, we'll take the second derivative, f prime prime of x equals minus 2. Well, this means that we have a constant rate of change of the slope, which means that the whole time this graph exists on the open interval, that it is always decreasing at the slope is decreasing at a constant rate, which means it's concavity down, because it's decreasing as we go from left to right, and that means that we have a maxima at x equals 0. So this is a maxima. And is it a local? Yes, it is a local maxima. Is it also an absolute maxima? It is, because no other point on the graph has a higher value than this point. All right, and last but not least, x cubed is an interesting one, because you'll notice on the graph there's no maxima or minima, but there's still a point at which the slope, the tangent slope, equals 0. So let's solve for when that point is, what the critical point is. So f prime of x equals 3x squared. We set the derivative equal to 0 because we're solving for places where there is 0 slope on the tangent, equals 3x squared, and we'll find that x equals 0 again. So we have a critical point at x equals 0. And then the question is it concavity up or concavity down? Is it a local max or a local min? And to do that, we're going to go ahead and take the second derivative, f prime prime of x, which is equal to 6x. All right, and we know our critical point, so you'll notice that there's no longer a constant rate of change of slope like we had in the quadratics. Now it varies linearly, which makes sense because we're one order higher, we're one power higher here. But when we plug in our critical point 0 for x, so f prime prime of 0, we get 0, because 6 times 0 is 0. What 0 means with the second derivative is that it's not a maxima and it's not a minima. It's actually a saddle point. So in other words, we're having our rate of change of slope decrease, then we're at 0, and then it decides to change its mind and increase. So that'll be equal to 0. Now, what if we're interested in, like, say, when x equals 1? Not because it's a maxima or minima, just because we want to figure out how this rate of change of slope is changing. So we would plug that into f prime prime, and we'd plug in 1. Well, that's going to give us 6. 6 is a positive number, which means we're concavity up, and you can see that in the graph here. And once again, if I do f prime prime of minus 1, I'll get minus 6, which means concavity down. So everything on this side of 0 is concavity down. Everything on this side of 0 is concavity up. And so I hope this is useful, and I'll see you next video.